Hello. Today we're going to cover the pre-lab for the heat exchanger experiment. In this experiment, the objective is to determine the suitability of our heat exchanger for use in a research project. They've asked us to characterize a number of items, and we'll start this pre-lab by going through the different items that we want to characterize. All right, the first one says they ask for us to evaluate the log mean temperature difference for each configuration. All right, in class we learned that the log mean temperature difference could be written as delta T1 minus delta T2 over the log of delta T1 divided by delta T2. All right, this is also equal to delta T2 minus delta T1 divided by the log of delta T2 over delta T1. Remember that these subscripts refer to physical locations, not the hot or cold flow. They refer to physical locations. All right. For parallel flow, we have that delta T1 equals T hot in minus T cold in, and delta T2 is equal to T hot out minus T cold out. For counterflow, we have that delta T1 is equal to T hot in minus T cold out, and delta T2 is equal to T hot out minus T cold in. Okay, in the experiment, you're going to be measuring T hot in, T cold out, T hot out, and T cold in both situations. So you will have that information, so you should be able to evaluate the log mean temperature difference. All right, the second part asks us to compute the product of the overall heat transfer coefficient, U, and the area A for each configuration using the log mean temperature difference. So in class we learned that UA, okay, we can either do it with the outer surface where we'd have U0A or outer also equals U inner, A inner. And we know that equals Q, the heat rate, divided by the log mean temperature difference. Okay, well we already have from part A the log mean temperature difference, so we need Q in order to get UA. Well, we also know that Q, and we can choose either the hot flow or the cold flow, is equal to m dot H CPH times T hot in minus T hot out. That's also equal to the m dot cold, mass flow rate of the cold, times Cp cold, T cold out minus T cold in. So we can choose either one of these. In lab, we measure the mass flow rate, we measure the hot flow mass flow rate, we measure the cold flow mass flow rate. We can look up the specific heats, and we also have measured the hot and cold flow temperature. So we can get Q, and then once we have that, then we can plug that into this expression and we can get UA. Okay, so that's how we get UA experimentally. Next we want to get UA, we want to be able to predict UA, so we want the theoretical UA. And so it asks us to calculate UA, we'll call it theoretical, or predicted, either one. It says use the appropriate empirical heat exchanger correlations and compare these with experimental values. So what we've also learned in class is that we have, this is kind of a long expression, we have 1 over UA equals 1, it could be U inner, A inner, It's also equal to U outer, A outer. And all of that, I'm going to write it down here, is equal to 1 over HI AI plus the fouling factor Okay, I'm going to write it the next down here. It continues. Okay, so this, the inverse of this, if we knew all these factors here, would be our theoretical UA. Okay, so in order to compute this, first of all, let's make some assumptions. Let's assume for theoretical purposes that the fouling factor is equal to 0. So then we're going to have, and then I'm going to choose as our reference area the, well, we don't have to choose anything yet. We're going to go 1 over UA is equal to 1 over HI AI plus the log of d0 over di divided by 2 pi k L plus 1 over h0 a0. Okay, well d0 or do, d outer and di or d inner are given in the lab write-up. L is given. K is the thermal conductivity of the inner pipe. So we can look all that up. So this term is easy to calculate. We can get the inner area from the diameter, and we can get the outer area from the diameter. The only thing we're missing are the h's right here. Okay, well we get hi and h0 from the appropriate correlations in chapter 8, which is entitled Internal Flow. You're going to need, you'll calculate the Nusselt number, and then once you have the Nusselt number, well, to get the Nusselt number, you'll need the Prandtl number and the Reynolds number. And then once you have the Nusselt number, from there you can get the H value. Okay, the next step would be to calculate the fouling factor. Okay, in order to get the fouling factor, we can use the expressions that we've already developed. We know the actual UA from the experiment. We know the theoretical UA that we just calculated. So the difference between those two, the difference between the inverse of those two would be the fouling factor. So first of all, as a first approximation, let's assume that the fouling factor on the inner surface and the outer surfaces are the same. All right, well then we can say that 1 over UA actual equals 1 over UA theoretical plus RFI double prime over A inner plus RF outer double prime over A outer. Okay, we just assumed that RFI and RF0 were the same. So what we get after some algebra, we get that RF double prime times 1 over AI minus 1 over A0 equals 1 over UA actual minus 1 over UA theoretical. All right, so then we can divide by this term here, and we get that the fouling factor is equal to 1 over UA actual minus 1 over UA theoretical, all divided by 1 over AI minus 1 over A outer. Okay, the next step in the lab is to plot the hot fluid and cold fluid temperatures versus axial position in the heat exchanger for the different flow conditions. Okay, so if we put X down here, and we could call this, we could call that 0, and we could call that L for the full length, and we plot temperature. For parallel flow, it'll look something like this. Well, but what we actually know at this point, the only temperatures that we measure are the inlet temperatures and the outlet temperatures, and we may have a midpoint, but we don't know the other temperatures in between. Okay, so we can measure the inlet and outlet temperatures. We'll plot those, but we want to be able to predict the intermediate temperatures along this line here. Okay, the way we do that is we have to use what's called to get intermediate temperatures, we're going to use the effectiveness NTU method that we talk about in class. Let's say we want to predict the temperatures at X over L equals 1/4. Okay, so in our lab, the lab asks us to predict the temperature at X over L at 1/4, 1/2, 3/4. I'll show you how to do it at 1/4, and then we'll do the rest of them. Okay, from theory, we have that let me write it small here so I can get it all up here. Okay, I'm going to multiply both sides by A0, and we get 1 over U0 equals A0 over HI AI plus RFI double prime A0 over AI plus A0 log of D0 over DI divided by 2 pi KL plus R F0 double prime plus 1 over H0. Okay, after some algebra, we go through and we divide out several terms. We end up with 1 over U0 equals D0 over DI HI we end up with that term. Okay, now from this expression, 1 over the overall heat transfer coefficient, we can see on the right-hand side that length does not appear. So the overall heat transfer coefficient does not appear on length, but depend on length. Let's come over here. Therefore, if we go to where x over L equals 1/4, then we can write that U0, A0 at x over L equals 1/4 is equal to UA for the full length that we already know divided by 4. This is what we know. This is what we're trying to find out. Okay, so we know that UA for x over L equals 1/4. Okay, so at this point, well, from the effectiveness NTU method, we can write by definition that NTU equals UA over C min, where C is equal to m dot Cp. And C min is the lesser of m dot hot Cp hot versus m dot cold Cp cold. Okay, well, if we know the number of NTUs and we know the ratio of C min versus C max, I'll write that up here. We can use either figure 11.10 or 11.11 to get our effectiveness. And this would be from the 6th edition of the heat transfer book. If you have a different edition, it could be a different figure. All right, well, we know that the effectiveness is equal to Q over Q max, where Q max equals C min. Let me write it down here. Equals C min times T hot in minus T cold in. All right, we've already done this. We know that Q is equal to m dot H Cph times T hot in minus T hot out. Okay, we can do that at the, do this at x over L equals 1/4. We can say that m dot H times Cph times T hot in minus T hot out, and we're going to pick that at the x over L equals 1/4 point. So this will be the hot temperature at the 1/4 point. That equals epsilon times Q max. Okay, well, we know everything in this expression except for T hot out at x over L equals 1/4. So we can do some algebra, and we get T hot out at x over L equals 1/4 is equal to T hot N minus the effectiveness times Q max divided by M dot H CPH. So this gives us the temperature at the 1/4 point. We can do the same thing for the half and the 3/4 points for both the hot and the cold flow. All right, the last thing we're asked to do is to calculate the uncertainty in our values, or actually in the uncertainty of UA. Okay, so what we measured all right, so we know that UA is equal to Q over delta T log mean. Okay, we measured Q, well, we got Q from our temperatures and our mass flow rate and our specific heats, and we also measured the log mean temperature difference. Okay, if we use the average of the hot and the cold heat flows, heat rates, we get that UA, we'll plug in all our values here, because we're doing an uncertainty, so we want to plug in all our experimental values. We get that M dot H CPH times T hot in minus T hot out plus M dot C CPC times T cold out minus T cold in divided by 2. This is the average heat flow based on the hot and the cold flows divided by our log mean temperature difference, which is delta T1 minus delta T2 divided by the log of delta T1 over delta T2. Well, again, for uncertainty, we want to write everything in terms of our measured values. Okay, so we didn't actually measure delta T, we measured the temperatures. So let's write it like that. All right, so for parallel flow, we have the UA M dot H CPH times T hot in minus T hot out plus M dot C CPC minus T cold out minus T cold in, all divided by 2, divided by, so delta T1 is T hot in minus T cold in minus T hot out minus T cold out, all divided by the log of THI minus TCI over T hot out minus T cold out. Okay, so we've written UA in terms of all our experimental values or values that we've looked up. All right, to get the uncertainty, we're going to use the root sum square method. Let's come over here. Okay, so let's let big XUA equal the uncertainty in UA, and then we'll let little x equal the uncertainty in each measurement. Okay, using the root sum square method, then we have to take the partial derivative of each one of these terms, measured terms, and multiply it by its uncertainty squared, and then take the square root. So what we'll have, this is a long expression, we'll have big UA is equal to, we're going to have a big square root here, so I'll just go ahead and put that to remind you that it's here. We'll have the partial of UA with respect to m dot h times the uncertainty in m dot h squared plus the partial of UA with respect to CPH times the uncertainty in CPH squared plus the partial of UA with respect to T hot n times the uncertainty in T hot n squared plus the partial of UA with respect to T hot out times the uncertainty in T hot out squared plus, I have to go to the next board, but it's all still under the square root. The partial of UA with respect to m dot c times the uncertainty in m dot c squared plus, so we'll keep this square root up here. Remember, it goes with the other one. The partial of UA with respect to CPC times the uncertainty in CPC squared plus the uncertainty, or the partial with respect to UA, or the partial of UA with respect to T cold out times the uncertainty in T cold out squared plus the partial of UA with respect to T cold in times the uncertainty in T cold in all squared. So we have to take the square root of 8 terms, I mean not the square root, we have to take the partial derivative of 8 terms, multiply them by their uncertainty, and take, add them up, and then take the square root. Okay, my suggestion would be to write the term for UA out in its entirety using MATLAB. And then with MATLAB, you can tell it to take the partial derivative using symbolically with respect to each term. Then you can copy and paste and put that into Excel. Then you'll have the formula in Excel for each partial derivative, and you can use your spreadsheet to find the uncertainty for each condition. The uncertainties for the thermistors and the flow rates are given in the lab write-up. The uncertainty in CP can be obtained using the uncertainties for temperature and the table. So you're going to look up CP in the table. You'll have a value for a certain temperature. Well, if you know the uncertainty of the temperature, then you can look on either side of that value and find out what the uncertainty in your CP value is. I strongly recommend that you develop a spreadsheet to enter your data and do the analysis with some sample numbers prior to coming to the lab. If you come to the lab understanding what you're trying to do, you will do a nice job on the lab and everything should turn out fine. If you come to the lab without having practiced the analysis, without having a spreadsheet made up, all you're going to be doing is just coming in as anybody can do that. I can take anybody off the street. They can come in and copy numbers. Then you take it home. You may or may not do a nice job. You probably will not do a nice job. So understand what you're doing before you come to the lab, and everything will work out fine. And let me remind you of the objectives of this experiment, because you have to talk about this in your lab write-up in the letter. You were to determine the suitability of this double pipe heat exchanger for a research project. Well, if you're going to determine the suitability, then you have to have some criteria for what suitable is. I'm going to leave that up to you to establish criteria. You need to establish some kind of criteria for what you consider to be suitability, and then you have to address that in your letter saying whether it met that criteria or not. Okay, now we're going to show you how to operate the equipment, and we'll move to the lab for that. Thank you. This is our double pipe heat exchanger. It can be set up to operate in either the counterflow or parallel flow configuration. The configuration is set up using these two valves here, which are labeled counter and parallel flow. The arrows point to the correct direction. Flow is measured using two rotary flow sensors, one located here, one located here. Temperature is measured using thermistors. We have two thermistors at the inlet or exit, depending on the configuration. We have two more thermistors at the other inlet exit situation. And then we have two thermistors at the midpoint. There is a hot water heater to provide hot water. Measurements are made using a data acquisition board, which is located right here, connected to this computer. To operate the equipment, first turn on the power supply and ensure 24 volts. Then turn on the computer. The computer's already on for this demonstration. Click on the icon in the center of the screen, the LabVIEW icon, and wait for it to come up. When it comes up, you're going to select the appropriate configuration, meaning either the flow type, either parallel flow or counterflow. Once you have that selected, click the Run button. Disconnect the computer from the line power by disconnecting this line here from this external battery in order to reduce noise in the system. Once you've done that, come over here, turn on the water at the main water valve and adjust the flow rate by looking at the flow rate on the computer screen and adjust these red handle valves. Turn on the hot water heater using this handle right here on the wall, and then we'll wait for the system to come to steady state. Steady state should only take a couple of minutes, maybe even seconds at the most. Once it comes to steady state, begin collecting data. You will collect temperature data at the inlet, the exit, and the midpoint, and you will collect flow rate. Do this for the various flow rates described in your lab write-up. When you're done with that configuration, come over here, change the flow configuration. In this case, parallel, I'm going to switch it to counterflow. The valves are kind of hard to turn. And reset the flow rates using the red-handed valves. Again, wait for the system to come to steady state. When it's reached steady state, record the temperatures and the flow rates again. When you're done, upon completion of the experiment, I would like you to turn off the main water valve over here on the left. Turn off the hot water heater with the handle on the wall over here. And open the red-handed valves so they're in the open position to relieve pressure on the system. If you're the last group of the day, I would like you to also turn off the computer and turn off the power supply. And that completes the double pipe heat exchanger demonstration. Thank you.